Wait, Reggie?
Real easy into polynomials a little bit today.
Really?
And you have your blue sheet with the dates on it, so, you know, register those on the calendar. And just know that there will be a dance party this period, okay?
What? I get to dance?
Oh boy, 2 minutes, okay? Alright, the first thing that appears on this slide is something that sometimes intimidates people because of this notation. But this is just our notation for a general polynomial, right, of any order. So, x to the n all the way down to a to the 0 times x to the 0, right? And we're using the subscripts a sub n minus 1 to label the coefficients. I know you might be like, can't we just use like a, b, c, d, etc. for the coefficients? I hear you. But first of all, what if you run out of letters? And that could be cumbersome or whatever. The other reason is actually, I think you're going to like it better, because if we name, like as soon as I say a3, you know that's the coefficient on the cubic term, the x to the third term. So whereas if I say like I, you're like a, b, c, d, and you're like, which is that? That's the coefficient on, I don't know, right? So you can see why that's better, even though at first it might look cumbersome. And I think your previous experience in life verifies this, right? That you know the end behavior of polynomials. So let's just test you on it. You know that polynomials can only look one of 4 ways as they approach, as x approaches infinity or negative infinity. And I have those 4 pictures here. So a volunteer will now tell us and remind us what must be true about the degree. Wait. The degree, it's not funny, okay. And the leading coefficient of the first one. Go ahead. Who knows that? A, B, take it away. He's right. What about the next one? Someone else. Good, yes. Very good. What about the next one? So I knew you knew this. This is meant to be review. Who else has got the next one? Reggie. What's the, what is even?
Oh, the third.
Well, but what is even though?
What is even?
But don't say it. What is even?
The graph?
No. No, it's not an even function.
N is even.
Which is what? What's n? 4. No, but what is the n? What is n? The degree, yeah. So the degree is even and the leading coefficient? You don't know? It is positive? Okay.
Oh, that's between the
Yeah. And what about the last one? You want to do the last one?
Yeah, I don't know if I tried that. It could be like a negative, a leading coefficient, and it's still a degree is still even.
Right. Right, so you understand that those are only the 4 things that can happen with polynomials out at their ends, at least, right? So, good. That's all you need. That's all you need in order to be able to do this dance. I know that you're excited. I can sense it. All right, I have the music all queued up. All right. You right? All right. So we are going to teach you. Some of you already, it seems, may already be a little bit aware of this dance, but think about the fact that you are going to be doing this in a second. Okay. Prepare yourself emotionally for this.
I'm already prepared.
All right, we are gonna dance. Before I play the music, though, we need to practice a little bit. If you guys could stand up. Go ahead. This is not optional. Stand up. Just stretch it out. All right, here we go. So let me teach you the dance for those who have never done it before, and then I'll hit the music. Okay, you ready? So we'll do without music first. I'm going to say the degree of a polynomial, and then we're going to do the arms in that manner. And we're going to do it positive and negative. I'm not going to say the word positive and negative. We're just going to do it. So I'm going to say 1 like this to follow along. 1, and we're going to do both. Positive first and then negative. It's a line, you know, right? Yeah, it's a good workout too, really. Okay. All right, then I'm going to say 2. I'm just going to say the degree, and then we'll do positive and then negative. Always positive and then negative. 3. You feel it? You're starting to 4, and you can get a little narrower too. 5. And then 6, get a little higher, reach up to the sky. 7, get a little skinnier. 8, 9, you're actually already starting, even without the music, you're starting to feel that rhythm, aren't you? Okay, here we go. Wait, don't sit down, here we go. Are you ready? Yeah. Are you ready? Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Keep going. It's beautiful. Where's the other one? Alright, wait. We'll start over in a second. Okay? We'll start over. Who wants to do it?
I want to do it.
Alright, I got one. Alright, here we go. This time we're doing it again. 1, 2, 3, 4, 5, and then move out a little bit. 6, 9, 10, 11, 12, 51. Woo! Woo! Everyone breathe. What? It's complicated. It's complicated choreography. All right, now do this problem.
God, I couldn't ask you this.
Oh, I'm sorry. I'm sorry.
Oh my god, I will pay so much. I feel attacked.
Alright, so do this, and this, and this. Oh man, you gotta come down from that, you know?
I don't think I can this weekend.
I know, right? I know.
P90X? What is
Good.
P90X?
Cardio box. Check. Cardio, check. You like that first? So you're writing two limits. The limit is x goes to infinity and negative infinity. Okay. Anyone? I'll take a volunteer on the first one. Okay. Tell me what you know. Anyone have a hunch how to finish these two statements on the first one? Two little things. Who can help me out here? I essentially tried to make it hard. It would be easier if it was standard form, wouldn't it? That would have been nice of me. Wouldn't it have been? That's okay, Jay, we can take it anyway though, maybe. Go ahead. Talk to us about it. Give us some insight into what you're thinking. All right, and how do you know that? Okay, so it is definitely an odd degree polynomial. Do you agree? Okay, so it's got to be one of these two. And how do you make the determination which it is? Oh, because of the negative 15. Okay, all right, wait, Aiden, yeah.
If you multiply negative 15 by negative x, you get positive 15x.
Wait, I have a question though about that, Aiden. Are you saying that, like, say I have this parabola, I love this parabola, it's my favorite one. Are you saying that that equals negative x minus 5 squared? Like, can you do that? Is that a thing?
Wait, what? Pam
No, Pam does.
But I like your thought. He's making sense, you think? What about it? Alright. But does that mean we have to actually, like, multiply this out? Like, what do we... Well, let's do it. Let's do it. Okay, this will be fun. Alright, so a bunch of those things, I'm trying to feel this out here. Help me out. Anyone have an idea of what that's going to look like at all? It starts with, do you agree that there's a negative x to the 15th in this product? Plus a bunch of other garbage. It's of lower powers, right? Alright, so I think we have it, don't we? Alright, so Jay, you want to revise your original statement? What?
Not even, sorry. It's going to be a positive coefficient. It's an odd, okay, it's this way.
Alright, can you give me the answers to this and this question?
So as x approaches infinity, yeah, h of x approaches infinity.
This one's what? Negative infinity. Alright, finally we sorted it out. This is pretty exciting. Did you test this out? Are you tweeting this? Are you live tweeting? I'm actually, the thing I'm hurt about is not that he's using his phone, but that you're not like instantly telling people that this is so exciting and you're not sharing it. You can put your foot away though if you want to. Alright, if you want, you know. Yeah, Reggie.
So because the coefficient is positive, that means that, so let's just, because x goes towards infinity, it will be a 1. Okay, so if it was negative, then it would be negative.
Then we'd switch these two answers. Yeah. Antonio, get the next one.
So the limit as x approaches negative infinity. So first of all, it looks like this.
How'd you know that? What are you going on with? What are you going on there? It's a cubic.
Yeah, but it's not a cubic.
But he says. It's not a cubic. Oh, you didn't fall for it, Antonio. You're making me. Okay.
Too smart.
You're too smart for that.
Yeah, so the power is even.
True.
Then the coefficient is negative.
So what's the answer?
It's as x approaches negative infinity, the limit is negative infinity.
Good. Here's a random question that doesn't seem to relate to anything else. Let's consider this one. Anyone have a way in on this last one?
Last one. Explain why it's not. What do you mean?
What's the? Who has it? I just wanted to buy you some time there. Yeah. What do you think, Juliet?
Well, because it's like has an odd power and its leading coefficient is positive, it's limit as it goes towards.
What you have a lot of its there. What are we talking about?
As the function goes.
What function? I don't see a function.
The end behavior.
But what function are you talking? No, I want to keep. I want to let you keep all that what you said, but let's clarify because you're right. You're right. I hear what you're saying, but can you clarify what function are you talking about? Or can someone else fill in the gap there? What function is she talking about? Yeah, Lisa.
X plus 2 squared minus 11x minus 12.
What, minus 11x minus 12? All right, so this equation is equal to, all right, now I think we have the function you're talking about in mind. Okay, keep going.
So as the x values go towards negative infinity, since they're positive, it's the y values are going to go towards negative infinity, and as it goes to positive infinity, the y values are going to go to positive infinity.
Okay.
And since like IVT,
Yeah, okay.
there has to be a point kind of where like it crosses at 0.
Yeah, all of that's some good thoughts. It's actually maybe two explanations there, really, right? One is that you wouldn't even have to talk about infinity and negative infinity and all that. If you could find, if this is continuous, if you could find just any value of x that gives a positive and a negative value, we're done, right? So that would work. You could just use the IVT from last unit. Or you also kind of mixed in there the stuff we've just been talking about. You know the range of that function is negative to positive infinity for any cubic. So it's got to include 0. If the range really is all reals, then it includes 0 also. Right. So something like that.
The one real solution then is 0?
Yeah. All right, so zeros of a function is a term I know you've heard before. By zeros, we sometimes also mean x-intercepts or roots. You've probably heard those. And for the most part, with a very, very small footnote, those can be used interchangeably. Okay, so you'll often hear us talk about find the roots or whatever. So just a little summer packet style problem here. Go for it. And in approximately 20 seconds, I'll call on whomever I like to give the answers. Because I think everyone should be able to do this. That's my thought, at least.
Oh, I remember this.
Whatever you're ready, Zach. Whenever you're ready. You got it? No, okay. Give me another second. Solving this equation.
There's 0 at x equals 0, and there's double root at x equals 5.
Only 2 roots. Okay, yeah. So what you factor this thing. Which is, in some ways, maybe not to a mature mathematical student like you, but in some ways it is a little surprising, to see that there are only 2 roots, maybe, or I don't know. How can that be? I mean, you kind of said that there's a double root at 5. So what does that say, though, about the graph? Oh, by the way, we didn't play with these enough yet. If you want to do like a quartic or something, you have to use the chin, like that, or the head. You know what I mean? So tell me about this cubic here. How could it be? How could it be that a cubic crosses the axis only twice? I'm not sure I get that. How could that look?
It doesn't fully cross it. It doesn't. So one of the times it fully crosses the x-axis, but the other time it doesn't fully do it. So it sort of just touches and goes with that.
If this is the x-axis and this is the y-axis here. So you're saying that it touches the x-axis at one of these 2 places. Okay, so which is it? X equals 5? So you're suggesting that it looks like this, not like this, even though that would also only touch the x-axis twice as well.
Yeah, I think it would be the first one.
You think it would be the first one, but you're not sure.
Actually, it would be the first one.
All right, rather than that.
Second.
In both cases, you'd have two values for x, where it crosses the x-axis.
You need 0, 0. So.
Well, yeah, no, it'll go through 0. I'm just suggesting here. I'll draw the picture. Maybe it's easier. I'm just asking, how do we know whether it's this, this, or this? Right? In both cases, we only have two places where it crosses the x-axis, or it touches the x-axis. Do you want to add your thoughts, Jasmine?
Well, you want to know between 0 and 5 if the values are either positive or negative, so you just plug in one value, like I plugged in 1, and then if you get a positive number by plugging in 1, then you would know it's the first one or the second one.
Oh, that's a great idea. Did you hear what she said? She said you could just plug any number in between this interval and see whether you get a positive or negative number, and then boom, we're done. It's got to be one of these two pictures. She's narrowed it down. I like that. Yeah. Antonio?
So since it's a double root, I think that means it has to like touch the x-axis and then like go up. Like there has to be like a local minimum at the x-axis.
Okay. You want to say one more thing, Jaden? Or no? Okay. Okay. Because, but I mean, that still begs the question, like why? But someone told you that once and you trusted them. Okay, that was a trustworthy piece of knowledge. But we should like think. All right, one last comment, and then I. What is moving 5 that way though? X cubed isn't moving 5 that way. Like part of it is, or something. Yeah, it's hard to think about it in terms of transformations, but I kind of hear you. All right. Well, let's keep thinking about this. It's not the last time, even today, that we'd like to say something about that. All right, can you find the y-intercept of this? And then we'll also talk about multiplicity of zeros in a second, which is what we've just been talking about. Yeah, that's a tricky one. All right, Shashir, help us out with the y-intercept. Wait, what?
So I get 0 for t.
That's a thing, okay.
You get -3 for the first thing, 1 for the next one, and then 4.
2 squared, yeah.
2 squared, 4. So then it's just -3 times 4, 12.
-12, yeah. Good.
Yes.
Now there are some people in this room, I will not say who they are, but who might have been trying to multiply this whole thing out. You know who you are. Which would in the end yield a correct answer. That is true. That is true. But this would be a little easier. You could still, anyone in this room still could multiply it out just for fun if you want. Just keep in mind what the definition for any function, what the definition of the y-intercept is. It's just you plugging in 0 for x, right? All right. What about this idea of multiplicity? I don't know if that's a new word to you or not, but certainly if you've heard of double roots or triple root roots, which it sounds like you guys already have, then you already know what this term means already. So if x minus a number appears in the factorization twice, then we call that a double root or a root with multiplicity 2. Or a triple root, we might say, is a root with multiplicity 3. And the thing that you already said is a rule that I'm going to put up here in a second. So we can broaden it, maybe. In fact, do you know how to broaden it? If it's a double root, you're right, it does touch. Can you generalize, though? What if it's a triple root? What happens? what kind of behavior does the function exhibit near that zero? In particular, I'm asking, do you think it crosses over or does it just touch and leave? What about the fourth? Jade, 10 imaginary bonus points to Jade. Right. So now that's an observation and a good guess, but I'd still like you to think about why that is true. Some of you started to articulate reasoning there, not just like authority. You're like, okay, someone told me. It seems like it should be true, but we do like proof and we like to have certainty about these things. It's math class after all. So I do want you to think about, that. Search your heart about why that might be true. And actually, I kind of like the idea of like plugging in some values. Was that you that said that, Jasmine? I kind of like that idea of plugging in a point that's like nearby on both sides and thinking about what would happen. We've got to lead to a fruitful explanation of this, actually. She doesn't know what I'm talking about, but she suggested earlier, so I thought I'd, yeah.
Also, if you plug in like a number that's in between those two zeros,
Uh-huh.
that's positive, that means that like touches, like the function is like what touches one of the roots. So one is like a double or triple root, and if it's a double root, and if it's a negative, that means that it crosses.
Yeah, if you get like, if it's positive on one side and negative, if the y values are positive on one side and negative on the other, then it crossed, right? Yeah. But you can maybe think, that's not the whole story. I think you need to think about it some more. But certainly it's true, what we've just said. And it does provide, you might be thinking that's kind of, something, I don't know, esoteric to think about. But it does actually provide a really good way of helping us visualize these functions if we obtain their factorizations. You can get a really nice picture of them, right? So let's just practice with another cubic like we were looking at earlier. Sorry, do you need? Wave loud. Did anyone wave wildly? Okay. Seeing no wild waving. All right, so let's practice by graphing this. And at this point, after our somewhat meandering discussion today, you should actually be able to know a lot about that polynomial. You're welcome that it's already factored. That was nice of me. But if it's in this factored form, you should be able to tell me a lot of things. Certainly what the zeros are, and put those right away on the graph. You should be able to tell me what the y-intercept is. Go ahead and put that on the graph. You should be able to understand right away what the end behavior should look like. So make sure that happens when you go to graph it. And lastly, the thing we just talked about, you should also know not just where the zeros are, but the behavior of the function at each of those zeros, whether it crosses or just touches. So give it a try. See if you can get a pretty decent picture of this factored form of this cubic. And while you're doing that, I'm going to look up a really moving passage in our book that I'd like to share. Yeah, but draw the picture. Moving. Huh? You?
It's one of the coats. Did I move you?
I know, but
Yeah, and she knows what you're about.
I'm body shaming you. Like the optical
And then
Who will graph it for us? Go. To the board. Young man. To the board. You should really report these right to the board.
The whiteboard or the actual board? Comparison of the board or
It's right here. Each side, everybody.
Thank you. Hi
All
everyone.
right, well, each side is graphing that. I'm gonna read this
Oh, it's already on the.
moving passage from our book. Okay. It doesn't use the word touch. Yep. It says the zero of multiplicity n greater than or equal to 2 is a repeated zero. Notice in figure 2.27 that the graph of f just kisses the x-axis without crossing it. So that's a term you could use too if you're interested in getting more intimate with the mathematics. I just thought I'd share that. Section 2.3 in the book, everybody. Okay.
You may now kiss the line.
You may not. Well, what does it actually kiss?
It sounds better. It sounds closer to Brad. Anyway, Joe, did you know that?
The last example we did, what was that? X minus. What was the last problem that we had up here? The y-intercept one?
Yeah, okay. Don't do that to me.
Minus 3? Or x plus 3? Was that what it was? X minus 3. Was that what it was? Alright, just for fun, let's graph this one too. Just for fun.
Yeah.
For the love of the game, you guys.
Am I good? Yes. All right. Okay.
How did Itai do?
Good.
Is it right? So notice how we took all these things into consideration. The y-intercept. You see if he has it right? Notice the x-intercept. See, he has those right. Notice the end behavior. It's a cubic, and its end behavior is the right to model a cubic with a positive leading coefficient. And notice that he has the action, the multiplicity idea right too. Crossing here, just touching, or excuse me, kissing here. Okay. All right. So how are we going to graph this? Let's do it. 1, 2, 3. -1. Also 1 at 2. True story. True story. And what kind of function is this? It's not even, but its degree is even. Yeah, it's a 4th degree. So maybe it has this kind of shape or something going up, right? Yeah, what's the y-intercept? We said -12, right? Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so what do we do? As I go to draw this, what advice do you have for me, though? Yeah. Crosses here, right?
Oh, be careful. Oh, be careful.
It doesn't necessarily have a minimum there, but whatever. And then what?
No. Oh, wait, no.
Something like that. I mean, the picture, you should graph it. You should graph it yourself on your calculator, and you can see that we're probably not right, but we're probably fairly right. You know, it's just not a bad picture. It's not a bad picture at all. We know, the point is, we know a lot about these functions just given the characteristics we talked about today. Homework number 1 tonight, this weekend. Have a great, relaxing time with your family.
Yeah. Sometimes
Ivana, did you do a quick question? Or you want to? Okay.
I have waited all
Bye.
week for this weekend.